Suppose we have a set A and a set B of equal size n, where each pair AB has an associated non-negative weight value. The aim is to find the optimum perfect matching, that is, every element in A is matched to a unique element in B such that the sum of the weights of the matching is optimum. When we say optimum, we typically mean maximum or minimum. You could try every combination of perfect matchings and record the optimum. However, since there exists n factorial combinations of perfect matchings, the naive method would take n factorial time. However, we can do better using the Munkres algorithm. So here's an overview of the algorithm, presented in 5 steps. To brief, steps 1 and 2 put the matrix in slack form, where the weight of each pair is the weight above the possible minimum. In steps 3 and 4, we check to see if we have found the optimal solution. This occurs when the number of covering lines is equal to n, the number of elements in A and B. In step 5, if our solution is not optimal, we augment the matrix to create at least another 0 entry.
Here's an example matrix with 4 workers and 4 different tasks. We're going to find the minimum cost of assigning the tasks to the workers, such that each worker has been assigned a unique task. For the first step, we're going to subtract the smallest entry in each row from all of the entries from that row. This is because, regardless of what worker 1 is assigned, worker 1 is going to cost at least 20. So we may as well subtract 20 from all of the entries in the row. The same goes for worker 2. Whatever task worker 2 is given, it is still going to cost at least 15. So we subtract 20 from everything in row 1, 15 from everything in row 2, 20 for the third row, and 25 for the final row. Now, for the second step, we're going to do the same thing for each column in the matrix. Like before, regardless of what worker is given task 1, it is still going to cost at least 5, and regardless of what worker is given task 4, it is still going to cost at least 10. So subtract 5 from everything in the first column, 0 for the second and third columns, and 10 for the final column. For the third step, we're going to need to draw lines across the matrix, covering all of the 0 entries, such that the minimum amount of lines is used. In this case, the minimum number of covering lines is 3, and this can be achieved with a line through the second column, a line through the third row, and a line through the fourth row. Now, for step 4, we need to check if an optimal assignment of zeros is possible. If the minimum number of covering lines is n, then an optimal assignment is possible. The minimum number of covering lines here is 3 and n is 4, so an optimal assignment is not yet possible, so we move on to step 5. For step 5, we need to find the smallest entry not covered by any line. In this case, this is 5. We subtract this number from each uncovered row and add this number to each covered column. So we subtract 5 from the first and the second rows and add it to the second column. This has created an additional 0 in our matrix. Now return to step 3 and redraw the covering lines. Now, the minimum number of covering lines is 4, and this can be achieved by covering column 2 and then row 2, 3, and 4. Since the minimum number of covering lines is now equal to n, we know an optimal assignment of zeros is now possible, so we can assign tasks to workers. Worker 1 has a single 0 in its row, so we must assign task 2 to worker 1. Worker 2 has zeros for task 1 and task 2, but task 2 is already taken by worker 1, so the only available 0 is task 1. Worker 3 can be assigned task 3 or 4. Either way, the result will be the same, so let's assign it task 3. Now the only available 0 for worker 4 is task 4. Now, all of the workers have been assigned a unique task, and if we look at the original matrix, it is clear that the minimum total cost is 100. Previously, we hadn't actually given steps to draw the covering lines or to find the optimal assignment at the end, because to a person, these are both trivial. But of course, if you wanted to actually implement the Munkres algorithm, you would need these steps to do these parts. So, here's one method of drawing the covering lines. Firstly, find a row or column with a single unlined 0 and no circled zeros, and circle it. If there is no such row or column, then just circle an arbitrary 0. Next, if the circle is in a row with one unlined 0, draw a line for its column. If the circle is in a column with one unlined 0, draw a line for its row. If all rows and columns have more than one unlined 0, draw a line for the one with the most zeros, breaking ties arbitrarily. This is repeated until all zeros have been lined. If the minimum number of lines is n, then the circles provide the optimal assignment. So let's work for an example of this. This is the same matrix that we drew covering lines for in the previous example. We drew a line through the second column and the third and fourth rows. For the first step, we must find a row or column with only one unlined 0 and circle it. Row 1 has one unlined 0, so let's circle it. For step 2, if the circle is in a row with 1 on line 0, which it is, draw a line for its column. So let's draw a line through column 2. Now, since not all zeros have been lined, we return to step 1. So now we need to find another row column with only 1 on line 0. Column 1 has 1 on line 0, so let's circle it. This time, since the circle is in a column with 1 on line 0, we draw a line for its row, and return to step 1 as they're still on line 0s. Both column 3 and 4 have 1 on line 0, so I'm going to circle the one in column 3. The circle is in a column with only 1 on line 0, so we draw a line for its row. Now we have finished as all circles have been lined. This gave us the same result as we found in the earlier example. The first step of this line drawing algorithm takes O of n squared time per iteration, as you must iterate through all workers and tasks to locate the unlined 0 entries. Step 2 takes O of n time per iteration, as you must iterate through the row and the column of the circle to find out how many other unlined zeros are present. Step 3 loops back to step 1 until all zeros have been lined. Since the maximum amount of minimum covering lines is n, this means that there will be O of n iterations. So the total time complexity of this algorithm is O of n cubed. The original Munkres assignment algorithm runs in O of n to the power of 4 time. However, Edmonds and Karp noticed it to be modified to run in O of n cubed time. Our pseudocode runs in O of n to the power of 4 time, and I'll explain why. The first step takes O of n squared time, because you must iterate through all workers and all tasks to first find the minimum values, and then subtract them from the entries. For this reason, the second step also takes O of n squared time. The third step, which consists of drawing the minimum covering lines, takes O of n cubed time, as we showed before. Step 4 checks whether the number of covering lines is equal to n, which takes constant time. Step 5 finds the smallest value that is not covered by a line and then subtracts this value from the uncovered rows and adds it to the covered columns. This takes n squared time, as it must iterate through the matrix, firstly to find the smallest value, and then to modify the entries accordingly. Steps 3 to 5 are repeated multiple times, and each time an additional 0 is created. In the worst case, after step 2, all of the zeros are in a single column, or in a single row of the matrix, meaning that steps 3 to 5 must be executed O of n times to create n-1 more zeros. So the total time is O of n cubed repeated O of n times, which is O of n to the power of 4.
Suppose there exists n elements in A and m elements in B such that n is greater than m. Furthermore, suppose we are only concerned with matching every element in B with a unique element in A. That is, we do not care if any elements of A are unmatched, so long as every element in B is matched. We can solve this problem using minimizing Munkres with some pre-computation. Before running Munkres, construct n-m dummy columns, where each entry of these columns has a weight value 0. This essentially adds non-existent elements to B that do not affect the final solution. Now run Munkres as usual. Any pairs in the minimum matching that involves any dummies we introduced in the pre-computation step can be ignored. The same idea can be applied to the case where there are more elements in B than A. Constructing n-m columns takes O(n) squared time in the worst case scenario. Thus running Munkres on a non-square matrix has the same time complexity as our original minimizing algorithm. Consider maximizing total gain as equivalent to minimizing total loss. With this notion, we can use our minimizing algorithm to solve the maximum weighted matching problem, with little extra pre-computation. Simply search the matrix for the maximum weight, which takes n squared time using a linear search, and let the new weight of each pair AB be the maximum weight minus the old weight of AB, which also takes n squared time. Now run minimizing Munkres on the new matrix, and use the resultant matching to sum the weights of the old matrix. Thus, the maximizing algorithm runs in the same order as the minimizing algorithm. And that's it.